Hello, chemistry students. We're continuing our discussion on equilibrium, and we're going to start with talking about the reaction quotient. That's Q. We'll look at what that means in a bit, but that's just testing whether a solution has reached that equilibrium point. We don't know sometimes if it has or it hasn't, so we're going to use our Q value and compare that to your known K or KEQ value. Right, let's get started. So, like I said, sometimes you don't know if a reaction has reached that equilibrium point. So you can measure concentrations at any given time. Right, and these then can be used to calculate a Q value, and that can be compared to K. Now your Q expression, your reaction quotient Q, would essentially look like an equilibrium expression in the same way, except the difference here is you don't know if these concentrations of products and reactants C, D, A, B are at equilibrium. So you then have to compare. Once you do find a Q value, and your Q value, your reaction quotient can be equal to KEQ, and if that's the case, well then we know that the reaction is at equilibrium. If Q is greater than KEQ, now think about what that means. What is on your numerator? We see that C and D, your products, concentration of the products to their exponents are in your numerator. So if Q is greater than KEQ, that means your products are favored, right? So it's not at equilibrium, right? It's not equal to. It favors the forward reaction, right? Because the forward reaction would produce, of course, products. And if that side is favored, it's not at equilibrium. So as a result, to get to equilibrium, the reaction is going to move to the opposite end, which in this case, if it's the preferred forward direction, right, what will happen then is it will move to the left to get to equilibrium. Now, if your Q value is less than KEQ, so it's not at equilibrium, of course, and it favors then your reactant side, noticing then that if your Q value is smaller, that means your reactants are favored because they appear in your denominator. So if Q is smaller, that means your reactants are favored, or in other words, it favors the reverse direction. So because it favors the reverse direction, this is the direction it favors, what will happen so that it reaches equilibrium is that it will proceed then to the opposite direction, right, opposite of that, which is the right side, or forward direction, okay? So here's a diagram that depicts just that. If Q is less than K, it's going to move forward to reach equilibrium. If Q is greater, it's going to move in the reverse direction so that Q can then be equal to K. Okay, example. We've seen this reaction many times now. Here's a sample of concentrations at equilibrium. We have a 4 molar concentration of nitrogen, and we have 2 times 10 to the negative 2 of hydrogen, 2.2 times 10 to the negative 4 molar concentration of ammonia. Right, so we're going to, and then a KEQ value so that we can compare what our Q value is. So we have to calculate whether the system is at equilibrium, and we do that by plugging in these concentrations into our Q expression, which is going to look very similar or exactly the same as a KEQ. So remember, all of these exponents, they come from the balanced equation here. So it's products over reactants, ammonia to the power of 2, nitrogen, hydrogen to the power of 3. Plug those in and look, we get 0.0015. Now, if we compare that to KEQ, we see that Q is less than KEQ. Now, if Q is less than KEQ, that means the denominator is larger, right? Larger than it should be. That means your reactants are favored, so it's going to move in the forward direction, right? It will proceed then to the right. It is not at equilibrium, it will move to the right. And that's essentially it. Right? Hopefully that's helped. Not too long today. Here's practice post questions you have.